My name is Jeremiah Fioravanti. I'm the president of the Delaware County Institute of Science. I'm a professor at Harrisburg Area Community College, HACC. I want to welcome you to our second virtual Zoom lecture of the winter lecture series. Again, I want to remind you that this is no small feat for an all-volunteer organization, which has been in existence since 1833. And we host lectures in person, and we will in the spring again, in our historic building in downtown Media, Pennsylvania, that was built in 1867. I want to take this opportunity to encourage you to become members, volunteer, donate, or contribute to help maintain the sustainability of our organization, as many volunteers have done currently and in the past. I'd like to thank Dr. Laura Gerton of Penn State for setting up this lecture, and Dr. Dan King of Drexel University for technical support tonight. And just remind you that we have another Zoom lecture, our last one of the winter, will be on February 13th, the same time, with Dr. Claire Rutledge, which will be a special treat because I believe she's presenting an international Zoom presentation for us. So without further ado, Dr. Gerton, would you please introduce our speaker?
Thank you, Jeremiah, and good evening, everyone. So I am thrilled to bring to Zoom this evening Shawn Dahl, who is a senior space weather forecaster at the Space Weather Prediction Center in Boulder, Colorado. And tonight he's going to be sharing with us a little bit about space weather activity, forecasting, potential impacts, and a little bit overall about what they do at the Space Weather Prediction Center in terms of their operations. So I'm just going to go ahead and turn it right over to our speaker.
All right, thank you to Dr. Gerton and everybody. Pleased to be here and give you a virtual presentation today about the space weather and the Space Weather Prediction Center. So as mentioned, I'm Shawn. I am one of the forecasters here. I'm talking to you right now from my house, and you can see by my backdrop that not only is the space part of my profession now, but it's also my hobby with my telescopes back here. So just if you were wondering about that. But I was just in there on a day shift today. It is a shift work job, as you'll find out as we go through this. But I was able to get back here in time to do this for you today. And I'm really pleased to be here. I love doing education outreach type talks. So with that, let's get right into it. So if you could be here at the SWPC in person at the Space Weather Prediction Center, you would normally be standing around, say, these two giant windows here, looking into the Forecast Operations Center, because that's really the heart of the Space Weather Prediction Center. Now, we are part of the National Weather Service, and the National Weather Service falls under the National Oceanic and Atmospheric Administration, NOAA for short, like the logo you see here on this slide. And as part of the National Weather Service, we're really proud to be part of that mission because it's looking out for the protection of life and property. Now, we all know that in regular weather, lives can be at risk, property is at risk, right? There's always, every year, unfortunately, deaths and severe damage due to severe weather. Well, space weather has its issues as well, but normally lives aren't at risk, although it can happen depending on what one wants to do with their life. Property can be impacted as well, but not here on the surface of our planet, but really property in space, as we will talk about when we go through these slides today. So why is it important? Well, we'll talk a lot about that, but the government already considers this very important, as well as private enterprise, those launching rockets into space, controlling satellites out beyond Earth, orbital probes going out through the solar system. NASA looks out for their benefit when it comes to space weather, to be looking out for potential impacts to those spacecraft way out there. We're responsible here at SWPC for basically that sun-Earth line. Anything happening here at and around planet Earth, as well as the moon areas, is pretty much what we're dealing with when it comes to space weather. Now, our government has all sorts of bills and legislation that's been passed over the recent years because they know how important space weather is to our modern day of life, because it impacts our technology. And you're going to learn a lot of examples of that today as we move through this presentation. So what exactly is space weather? Well, simply put, this is about as simple as I can make it. It's really about what's taking place on that giant ball of burning gas 93 or so million miles away, what's happening between that, in that interstellar space between the sun and here at planet Earth, and ultimately at and around our planet. Now, you all know what regular weather looks like. You know what a tornado is. You know what a blizzard is. Well, what does space weather look like? Well, it's things like this, things that sound like they came out of a science fiction movie. We have coronal mass ejections, geomagnetic storms, solar radiation storms. These are some of the examples of space weather storms and other things on this slide comparatively as well. And my goal here is to get you very familiar with almost everything you're seeing right here on this slide as we go through this talk. But before we get into the space weather events themselves, let's look at some of the impacts. Now, impacts can be very wide when it comes to space weather events, but this slide does a pretty good job of encapsulating the most common technologies and things that could potentially be impacted by space weather. It's still quite rare for a space weather storm to impact something dramatically to the rate where it could be perhaps catastrophic, but it does happen, as rare as it may be. Now, some of the things to focus on here, some of the things you're seeing, we see the power grid. Well, that is the #1 driving factor of why we exist as SWPC, as this organization right here. It's because of the effect that space weather could potentially have in the most extreme circumstances on our power grid. Also, manned space flight. You're going to learn how rocket launches can be scrubbed when it comes to a space weather storm, why they don't want to take the risk of going up into the atmosphere when one of these events is happening. How HF communication can be dramatically impacted, and airlines still rely on that today when they're doing transit oceanic flights, especially across the Atlantic Ocean in particular. We see rail pipelines can be impacted. They can be degraded over time due to severe geomagnetic storm events that like to ride and take those shortcuts and get on things not only like power grid or rail lines, but on pipelines. Things one might not even think about are the types of things that space weather could potentially impact. So what does this all actually mean, and what is it that SWPC is actually doing? Well, first, let's talk about the people that we have here. I know a lot of you are looking at a career, maybe something like this is something you're interested in. Well, when it comes to the Space Weather Prediction Center, as I mentioned, we are part of the National Weather Service. We're one of the national centers in the Weather Service. There are 9 of them. The Hurricane Center is one you're quite familiar with. Maybe even the Severe Storm Center you know about. But we are SWPC, we're one of them. And we have all sorts of people, as you see on this slide, that are involved, all sorts of professions, from administrative support to information technology support to engineers, all the way up through world-renowned scientists, which is one of the outstanding, most interesting things about working here at SWPC, is that we have some of the most knowledgeable doctors and professionals in this profession in areas. So if I have a question or I want to learn about a little bit more, say about a coronal mass ejection or something that I'm seeing and trying to understand something a little better, hey, I've got several people I can walk upstairs and go talk to them, ask them questions, or invite them to come down really quick and help me sort something out. That's not something that's readily available at any forecast office in the Weather Service. But it's really cool that we have these people right here at SWPC for us to engage with. We're doing research to operations and operations to research ventures. We now have a test bed in SWPC as well that's getting spun up. What that basically means is we can run model experiments in there. We can run scenarios and tests with organizations. Last fall, we just had the aviation industry here because space weather has become more important to think about and involved in planning and actual flights for certain types of advisories we're now putting out as part of an international global effort. And they were all here for a week long, and we were going through and engaging with each other about their needs and wants and informing them and educating them. So that's pretty cool that we get to do that as well. And we're really the world leader when it comes to space weather observations, tools, and resources. We really started this business. One of the pre-questions that I was just given was about how long has space weather been around as a profession or an interest, an educational item? Well, all the way back in the 11th century, I think it was, there were space weather observations kind of going on. The Chinese were able to encapsulate some sunspot drawings that they could see somehow through maybe the smoky horizon, but they also observed a supernova. Galileo was drawing and examining sunspots. So we learned throughout history, but as far as an actual profession and science goes, it really started coming up closer to and around Skylab when astronauts discovered one of the features we're going to talk about, coronal holes, while they were out there in space running their experimental packages and running their equipment. Now, the forecast office is just one of the entities, one of the parts of SWPC, but it is the focal point, as I talked about. So if we could go behind those two giant windows and go into the center, what you're seeing on this slide is pretty much what's there as I walked out the door today. Giant monitors on the wall, monitoring the sun and all sorts of different temperatures and wavelengths of light from several different satellites in space. And we are there. Somebody is always staffed in that office 24 hours, 7 days a week, regardless of the time and holiday, doesn't matter. We all rotate through our shifts. We do 2 weeks of one, so I'm currently on the day shift, and then eventually I'll rotate to the evening shift, which runs from 3 in the afternoon until 1 in the morning, and the night shift is there from 8:30 at night till 6:30 in the morning. That's just the nature of weather, whether you're doing terrestrial weather as an operation or space weather as an operation. And in particular, when it comes to space weather, even when the sun is in its lowest levels of activity, it can still put out significant events. So we always have to be there, ready to go, putting out our forecasts and looking out for any alerts, watches, and warnings, which is, of course, the most priority-driven part of our mission. Now, we have a lot of important partners that we work with. The rest of the world has spun up centers similar to ours, but they're really focused more on their national interests. Our national interests are very global, all the way into space. So that's what we're focused on. And when we come to partners, the US Air Force, my old profession for 22 years, doing meteorology and space weather, and even the spy world in West Berlin when I first came in the Air Force, but I won't get into that. But yes, the Air Force is a huge partner of us. They have observatories. I was stationed at one for 4 years on the island of Puerto Rico. My job, believe it or not, during that 4 years was to go to a solar observatory and monitor the sun, draw sunspots, report on solar activity and what we call hydrogen alpha light, looking out for those flares. NASA is a big partner of ours, a core partner. We talk to them every day for the sake of the safety of the astronauts on the space station. Who we're talking to are the scientists in this space radiation analysis group, looking out for their safety. You can see Canada on here, USGS, that's the Geologic Survey, National Science Organizations, Met Office over in the UK, the United Kingdom. We talk with them frequently and help work on forecasts and sorting things out. So wide variety, and it continues to grow. What kind of tools do we use? Well, I already talked about satellites in space. They have weather data packages on them for monitoring space weather. They have optical telescopes on them that can look and take images of the sun for us to look at for activity. There's observatories on the ground. I mentioned the Solar Observatory at Puerto Rico. That's what that thing on the top right on this slide is. That is the solar telescope I used in Puerto Rico for 4 years. It's just a ball turret, and it follows the sun from sunrise to sunset, and it projects it all the way down the tube into our dark building, and then goes all sorts of different places so we can look at images in white light and through these special filters for hydrogen alpha. We have the satellites as part of the GONG network, which falls under NSO. Same types of thing, telescopes that monitor the sun in hydrogen alpha light or look at it in white light and can run magnetic maps of the sun. We'll learn about some of that as well. And then we have other satellites in space, anywhere from 20,000 or so miles in a geosynchronous type orbit, all the way out to 1 million miles from Earth. It's always between the sun and the Earth. So it's always there as a kind of a space buoy, a perfect place to see what's coming towards us from the sun. And also some that NASA launched that went around the sun, believe it or not. Unfortunately, it's now almost back in line with Earth. And I say unfortunately because when it's on the side of the sun as it was coming back around, it was great because we'd get another perspective of space weather storms and we could help figure out where these events are going, especially these things called coronal mass ejections. So that's kind of some of the tools that we have. Very expensive resources, right? But also there's not many of them. For those of you that are very interested in engineering, look what goes on here on this slide. SWPC in the center, we have satellites sending data in here to SWPC directly. They're sending data directly into other areas of the states that get filtered over here to SWPC. And we have information going out to the power grid industry, to NASA, other government agencies, especially FEMA, DOD, Department of Defense. We have magnetometer networks monitoring the Earth's magnetic field and changes going on. Gong I've talked about. Look at all this. Satellites in space 1 million miles away, and we're getting information filtered directly into our center. And much of it can happen in less than 5 minutes. Absolutely incredible how our technology is helping us get space weather information. And we're able to quickly look at it and quickly investigate it and quickly get out any watches, warnings, or alerts that need to go out or forecast adjustments. Very complex system. When part of it goes down, we run into big trouble, even just a small part. But it's amazing because we have, the Earth rotates, right? So some of these satellites can only be seen on the sunlit side of our Earth. So that's when they're being tracked and sending data in. And then it has to switch to another entity, say in Germany, and then over to North America on Wallops Island, and then over to South Korea or Japan or Australia. Very complex network. But the fact that we can generally, when things are working great, get all that information very quickly in this whole complex arrangement. So if you like this as part of your profession as an idea, wow, a growing industry and very fascinating, and still so much to learn when it comes to constructing platforms for us. The main driving factor of what we do is sending out, like any terrestrial weather forecast office looking out for your safety, is watches, warnings, and something else called alerts. So in our case, we put watches out generally 1 to 3 days in advance. And we really do this only for geomagnetic storms because we can forecast that far in advance for those things. So we'll put a watch out no sooner than 3 days out and no later than 1 day out. When something is imminent or about to happen, we'll put out a warning. So that works a little different than the terrestrial weather warning, which means that something is imminent or has been reported to have happened. That's where our alert comes in. It's happened. So a watch is well in advance. Warnings for when something's imminent or about to happen. We can get minutes to hours of notice here, and then the alert when something is actually happening. And now we're doing advisories as well, but our advisors are really centered for the aviation industry. And those cover even different categories, but I won't really get into that part today. So what are we forecasting for exactly? Well, we do impacts-based forecasting. That's something the Weather Service is really striven to do, which is more rewarding for customers, really knowing more about not only the weather event, but what does it mean to them? Will that bus be able to get kids to school safely in the morning, or is the blizzard going to be too much? They have to make decisions, right? So that's the impact-based decision forecasting. For us, we've always been doing it this way. The Weather Service has evolved to it, but we've been doing it this way for some time. So what is it that we're doing? There's many things that we're forecasting for, but there's 3 main categories. We're looking at solar radiation storms as it relates to solar energetic proton events. We're looking at HF radio blackouts as it relates to solar flares. And we're looking at geomagnetic storms, with the cause of those being coronal mass ejections or coronal holes in general. And we have a scale that we try to utilize for that. You saw it in the previous slide as well. It's a 1 through 5 scale, and it's adapted for these 3 main categories. The S is for solar radiation storms, the R for radio blackouts, and the G, obviously, for geomagnetic storms. So the 1 is the minor end of it. There's levels we're warning for even below that. But it's really when we get to that level of activity that now we're into the NOAA space weather scale category. And this goes all the way up, as you see, all the way up to the severe and extreme ends, that extreme being that 5 end, the most rare, but also the most likely to cause an impact, as rare as it would still be. So how does this relate to terrestrial weather? Well, we do the same thing. Most of us that work at SWPC, we're all physical scientists that do this function as forecasters, but most of us have a meteorology background of some kind. So we've been forecasting regular meteorology for years or decades in my case. We do the same things. You've all seen weather maps on TV. You've seen this. So here's what I have, a synoptic weather map on the left, analyzing for low pressure systems, high pressure systems, cold frontal boundaries, looking at these isobars, all these things. Space weather, we're doing this for the sun. We try to do a synoptic map of the sun, and we do this twice a day. And we're focused on features as well. Things like coronal holes, things like sunspots, things like, instead of fronts, we're looking for that neutral area of magnetic field lines. These are the types of things that we look for and outline on our synoptic drawing. And it makes us and allows us as a starting point to kind of go through all the steps that are normal, as you see here, for forecast processes. I know there was a pre-question here as well about does space weather affect terrestrial weather? No, it does not. Climatologically speaking, in some cases, depending on where we're at in the solar cycles and how long they last at a certain level, there is some possible correspondence there to how solar cycles went over time and what that may mean to certain types of climate patterns here on our planet. That's still being investigated. But in general, if I have a solar flare kick off like I did today, is that going to impact any terrestrial weather? No, it will not. So what is it about the sun? Before I can talk about space weather storms more, let's understand the sun a little more. It rotates as well. Every 27 days on average, it makes a full rotation. On average, I say, because it rotates differentially, meaning at different speeds. So the equator of the sun is going in about 25 days to come back around, but the polar regions of the sun are taking closer to 35 days. 10 days difference. Now the sun doesn't tear itself apart because it's held together by its mass, its gravity, and it can take it because it kind of acts like liquid dynamics. It doesn't tear apart. It's burning gas, plasma. But what it does mess with is its magnetic field, because the sun has one just like Earth, but the sun's magnetic field is never perfect like Earth's generally is. It really twists up over time because it gets pulled. So the magnetic field of the sun, let's pretend it was a nice, easy north-south line. Well, a month later, because the sun's equator is rotating faster, that gets pulled. And this happens again, month after month, it stretches further and further where it begins to wrap itself up and lap itself like NASCAR race car drivers going around a track. This is what happens on the sun, cyclically, almost to the very similar to Old Faithful. On average, about every 11 years, we get to the point where the sun is all wrapped up and twisted up and the magnetic fields are all littered all over the sun in all sorts of varying amounts because it's a messed up magnetic ball at that point. And that is solar maximum. So about every 11 years on average, we have a solar maximum. In between, not much is happening. The sun is more neutral. It's kind of reset itself and we're at solar minimum. So the last solar minimum was in about December of 2019. So now we're working our way up solar cycle 25. About 2 years or so from now, it's expected to be solar maximum. And already we're ahead of the forecasted curve. I guess we're still within the margin of error, but sunspot numbers are higher than currently forecast. What does that mean? I don't know. The sun could suddenly not do too much, or it could continue to build up. But that is the 11-year solar cycle. So when we get into those periods where the sun has become this messed up litter box of magnetic field lines and clusters, that's when we get these giant sunspot groups can begin to form. They can form even during solar minimum, but they're not really generally going to be very strong. So what you're seeing here is obviously the sun rotating. If it was solar minimum, we could go months and months without a single sunspot in the sun, and you wouldn't even be able to tell it's rotating. But here you clearly can see that. And look how these sunspot groups are changing. They're very dynamic because what's happened here is strong magnetic fields have punched through the surface of the sun. That surface being the photosphere where light finally escapes and makes its 8-minute journey here to Earth. That's where we look for sunspots, is in that photosphere. And so on this, look at this giant complex in the north hemisphere of the sun. Look closely and see all the little changes going on. There's magnetic fields embedded within magnetic fields in here. They're all over the place and they can get very complex in some cases. And it can be very hard to find that dividing line. More complex groups generally means more stress, which generally means more likelihood of a flare to happen. So when I was in there forecasting today, the sun had 6 visible sunspot groups on it, 3 of which were very impressive, all in the southern hemisphere right now. Somewhat complex. We just had a very large flare while I was in there today as well, but I'll talk more to that here later. But point being, we analyze, that's kind of our starting point, is looking closely at these sunspot groups, looking at their magnetic signature to see how complex they actually might be. And these can get very large. About 109 planet Earths can fit side by side across the sun's equator from limb to limb. This one's big right here on this picture. But here you can see a little more detail about these sunspot groups. So if you use your imagination, just envision here magnetic fields coming in and going back in all over the place amongst the sunspot group. So we're looking for those fields coming out of the sun and where they go back in. So that's kind of our positive and negative ends of the magnetic field. And that's what we're looking for when we map these regions. And then we can classify them. Just like one in biology class might classify an insect order or something like that, trying to identify an insect, or a plant in botany class. Same thing here, we have a classification scheme that we use for sunspot groups. So when we call it a certain type, the rest of the world science community that does this business or as a hobby knows exactly what we're talking about. The cool thing about SWPC is we drive the designation for these sunspot groups. So these sunspot groups, when we feel they've been around long enough and looks like they're going to last, or they've been flaring or something, we will give them a name, and that name is a 4-digit number. It's sequential. It'll start over back to 0001 when it starts over. And the rest of the world recognizes it. So if I was talking about sunspot group 3403 here, and I was talking about its classification or its flare potential, the rest of the world would know exactly what I'm talking about and where I'm talking about. So when we give it this name, this number, the rest of the world recognizes it as such as well. It's kind of cool that we drive that throughout the world community in this profession. So if we were going to number any of these other ones that you see on this particular image right now, well, that'd be 3406 would be the next one. So solar flares. Now we're getting into the solar storms here. So it's these complex magnetic fields. So if we just imagine my fingers here as a set of magnetic field lines all twisted up, coming in and coming out and back into the sun. Well, when they get overstressed, something has to give. Just like taking a rubber band and stretching it, stretching it, stretching it. If you stretch it too far before you let it go, it's going to break. And the energy is going to slap back at you. Same thing here with sunspot groups, something similar. It stretches and they stretch and they get stressed out. Boom. Something kind of breaks, but it doesn't break and become useless. It doesn't work that way in physics. It just instantly reconnects into something less stressful. But that can release tremendous amounts of energy when it happens. And if it does so, we can get this thing called a solar flare. This blast of electromagnetic energy through much of the spectrum that we can look at, and we measure these in X-rays. So we can't do that from the surface of our planet because the atmosphere filters out that X-ray energy. But it does affect the outer atmosphere. So we use satellites. On the GOES satellite, the same one that takes pictures of all the clouds that you see on TV all the time. That's the satellite that has our package on it and measures the sun in X-rays for us. And then we can classify it based off that strength. But because the atmosphere filters that out, it's working, it's heating up, it's becoming ionized. I can't ever say that word right. Ionization is happening. And that's what can cause radio blackouts to happen, which I'll talk about here in about another slide or so. But let's look at a flare in action. Man, something like this just happened today, except it was closer to the southeast limb of the sun. The southeast, by the way, the directions on the sun, when we talk about them, are not what you're used to on a map. So the east part of the sun is on the left, and the west part of the sun is on the right. Just think of it as it rising in the east, setting in the west. Maybe that'll help you. But this is what we look for. We're looking for these solar flares, and then we measure them, and then we can try to figure out, what does that mean? We can tell almost exactly what it means based off the strength of what it's doing to our atmosphere. So this slide may look a little complicated, but let's make it simple. X-rays are what we measure the sun in. It always has a background X-ray flux. That number is usually down into that A category you see on the right, or the B category. When we get to the sea levels, now we're having a flare, or that's our background levels like it is right now, because the sun has got a lot of spots on it, a lot of energy, a lot of X-ray flux. But when we get into the M class levels on the right, now we're into our NOAA space weather scale. So M1 through M4 is an R1 event, and M5 through M9 is an R2. You get into X1, now we're in the R3 level. That's what we had today, an X1.9 flare, an R3 event, a strong event. X10 would be severe, and X20 or higher is extreme. That's how this scale generally works. Now we forecast the probability that a flare can happen, but we cannot warn on them. We have no way of knowing that a flare is imminent or about to take place. So no watches, no warnings, but we do, and we don't do watches because once we get to activity going on, we'd have watches going on for days and days and days and days. So it's really the alert. So once we get to the M5 category, we send out an alert, and we won't do it again until we reach a certain level and it comes back down, and then we'll send out a summary message which describes the flare in much more detail. So one of the impacts that this has is on our outer atmosphere, especially in the area where radio waves in high frequency are refracting off the atmosphere and talking long distances from one country to another, or an aircraft out there out over the middle of the Atlantic Ocean trying to communicate with air traffic control. They'll often use HF as well, especially as a backup. It's really what they're often limited to when they're around the polar regions. But when we have a flare, like you see on this example right here, you don't see the flare in this picture, but look at that bottom left picture. What that is one of our models. It's called the D region absorption product. And what that is measuring the effect on the D region is really where these radio waves bounce off of. A flare from 2017, that red area, that made it almost impossible to communicate in HF radio over 2 continents and over the Atlantic Ocean and much of the Pacific Ocean. That's dramatic effect that these can have. The one we had today, because it's winter here right now in our northern hemisphere, this really was more of a southern hemisphere effect, and it kind of reached its way out from where the sun was directly overhead. But this can be very impactful, especially if you think about it in these terms, when it's combined with a terrestrial weather event, like happened here in 2017, hurricanes have just ravaged through the Caribbean islands, destroyed infrastructure, tore down telephone lines, pulverized cell phone towers, electric lines were ripped apart. There was no way to communicate. So what did they do? HF radio, ham radio spun up to be the emergency method of communicating. They couldn't do it because this solar flare, the largest one of the previous solar cycle, was going on at the same time. And it was impactful for over an hour because of its intensity, and it was slow to come down. That's how this can be impactful. Here in Colorado, it can impact us a lot as well. It's avalanche season. People are supposed to wear GPS responders on them. Certain things can make it difficult for them to find. Does a solar flare do that? Not necessarily, but another one we're going to talk about later can. But HF radio is important to the airlines. It's important to emergency responders and search and rescue people fighting forest fires out there. But those that are communicating, talking to each other, trying to find the person buried in an avalanche, they'll often use HF frequencies. So this is why this is very impactful and can be, well, life-threatening in some cases, not because of the event itself, but the effect that it's having. Here's an example from a air traffic control related weather unit and some of the experiences they were having during this flare. People couldn't communicate in the aircraft. There was garbled. In some cases, they just cut out. Imagine you're trying to land at an international airport. Fortunately, they don't talk via HF radio during that time, but this is how these things can be impactful. Just more information about it when it came to the hurricane network that was monitoring hurricanes, sending out information and observations. Weren't going out, weren't making it. Solar flares, and not even just flares themselves, but the sun is also monitored in radio. The Air Force does a great job at this. They have radio observatories that are monitoring discrete frequencies. And when we have solar activity happening, it can oversaturate what they're looking at. And that's when you can start to go above levels. And think of it this way. Radars that are important to our national defense that are looking over the horizon. If it happens in just the right way, at just the right time, at just the right intensity, it can look like jamming on that Department of Defense radar. That's important. This has happened in history in the past. If you look up Dr. Dolores Knipp, she's given some talks on an event back in the 60s, I believe it was, where nuclear war was a possibility because of a space weather event. It looked like jamming going on a mass scale. Air traffic control can be impacted by this. This is what this solar storm knocks out flight control headline is on the top of this. If the radar is looking across the sun at just the right time, when one of these events are going on at just the right angle, it can look like jamming. They can't see anything. Imagine this happening in Dallas, Fort Worth, or JFK in New York, some critical giant airport. That's kind of frightening if all of a sudden the planes can't be seen. So these are the types of things that space weather impacts that we may not even think about. Solar radiation storms. This is where physical harm can happen from a space weather storm. Not to us, we're fully protected by our atmosphere and our magnetic barrier, our magnetosphere, which acts like a shield for us. But rockets going out there, they can be impacted. Astronauts in space can be impacted, particularly when we go back to the moon. We just finished the practice scenario over the whole duration of this Artemis mission that just went to the moon and back. We were talking to our colleagues at NASA and other moon to Mars scientists about potential for these types of storms to practice what we're doing. So when we actually send humans out there the next go around in maybe 3 years or so, I guess when that is, that's the next solar maximum. We'll do a better job at predicting these events because they won't have shelter they can take. Airlines are impacted by these because of the effect they can have on communication as well. They can wipe it out around the polar regions, absolutely wipe it out, make it a complete blackout for days when we have these events going on. Satellites can get impacted in just the right way by these energetic protons, which are the driving factor for solar radiation storms. Very rare as it might be, but when it happens at just the wrong place, the wrong time, or in this case, the right place at the right time, it can cause an upset on the spacecraft or the satellite. And that upset can be bad enough that they can't control it anymore. They can't communicate with it, and now it becomes space junk. This has happened in the past. We're going back to the moon. These astronauts, I'm going to go ahead to this next slide. Look at the bottom right. That is talking about a solar proton event, a radiation storm from the early 70s. This happened right in between the last 2 Apollo lunar manned missions. If this had happened while astronauts were on the moon, it did not. But if it did, this would have made them very sick. They would have suffered very strong radiation sickness. And some believe it could have been lethal. That's what we're talking about when we go back to the moon. And if you ask me a question about what they're going to do, I can tell you. So somebody remember to ask me that question at the end, what the astronauts are going to do out there when they're beyond our atmosphere and our magnetosphere to protect themselves during these events. So let's go back to this slide. So same type of thing. Here's our scale examples. The first level scale, by the way, the amount of space that we're measuring for these events is very small, and it's usually less than 1. We're kind of more closer to 0 on the number of energetic protons that the sensor is picking up. When we get to 10, we're at S1, and then times 10 from there on out. So 100, we're at S2, 1,000, S3, and so on. By the way, that's a solar radiation storm on the far right that hit an optical sensor on one of the satellites that we rely on to look for space weather activity. It looks like a blizzard hit it, right? That is energetic protons in action. And this will scrub rocket launches because they don't want to risk being hit by any of these energetic protons that are now driving deeper into our outer atmosphere and causing an upset on the rocket components, because that would lead to catastrophic failure perhaps. And that means it's going to go off course and the stress is going to make it blow up. So these will not launch, even at the lower levels of these activities. Depends on the health of these and durability of these rocket platforms. Just another example, the Air Force will not launch these. SpaceX will not launch these, and these entities call us. SpaceX calls us frequently when it comes to their rocket launches to get more information for our forecast. What else are we looking for? We're looking for coronal holes because these can drive solar wind speeds, which are always coming out from the sun, can double or even triple the levels of speed. And that can push on our magnetosphere and cause currents to generate up and lead to certain types of storms that I've yet to talk about. And here's a coronal holes just kind of going with the rotation of the sun. These are these dark giant areas. These are where magnetic field lines are coming out of the sun, going all the way out to space before they come back and reconnect to the sun. So it's not all just localized magnetic fields. They can go further out into space as well. So we as forecasters, we analyze these very closely because we know these are going to be an increase in solar wind speed if we think they're actually going to magnetically connect to Earth. Just like any barometer or wind speed sensor and anemometer, we map from our instruments as well. Solar wind speed. In this case, you can see on the yellow plot in the middle, normal background speed of the solar wind when nothing's going on is anywhere from 275 to 375 kilometers per second. You can see the increase here went up to 600 kilometers per second, basically double the normal speed. That's a coronal hole. It also compressed the magnetic field that we're always measuring. You can see that on the top plot with those white and red markers, and I'll talk more about that in another slide. But just as an example. What else are we looking for? We're looking for filaments and prominence, these enormous giant features held by magnetic field lines that can really go out into space from the sun. It looks like a horseshoe magnet sitting there, and that's kind of what's going on in a way. So we as forecasters, we see these features. Sometimes they just sit there stable and nothing happens. Other times, because of these changes going on, the magnetic field's holding them in place, they can become active. They can start to move around and change. They can expand. And then if nothing really happens and you get a reconnection event that's nice and smooth and nothing trigger happy happens, well, gravity can just pull it all down harmlessly back to the sun and nothing extraordinary happens. But sometimes the energy and the extraordinary happens, and then these filaments and prominence can rocket off into space like me letting go of that rubber band. The difference here is it's carrying billions of tons of solar plasma out into space, and it's taking a strong localized magnetic field and sending it off into space as well. That's what really drives some of the storms if and when they arrive here at Earth. So what does something like this here look like with one of the instruments we have in space? It's called a coronagraph. If you've ever seen, and you can also see the flare, by the way, that happened in conjunction with this event. If you ever seen a total solar eclipse picture or one in person, that corona is what you see. Coronagraph is just an artificial way of creating an eclipse so we can look at the sun. This can be done very well in space, and that's what you're seeing here. This is about 1 million miles from Earth, and there's the corona. That white circle is the sun's diameter. Now focus on that top left bright area. The sun has these all the time. They're called streamers. And then also look at that plot in the bottom, that 9:30. That's the time. Look what happens in just 4 hours here. This is a coronal mass ejection. Billions of tons of coronal material and even thicker plasma material, even maybe even chromospheric material, have rocketed off into space. And look how that expanded in just that 4 hours as it departed the sun. These expand as they move out into space. So just because we see these on what looks like the side of the sun, limb, perimeter, doesn't mean it's just going that direction. Its expansion, 93 million miles is a lot of expansion time. It could still clip planet Earth and affect us here. But sometimes it's a little bit more obvious, and we can get these things called full halo coronal mass ejections. Now it looks like we're looking down the cannon, if you will, and you can see that material as a full halo. It's only going one of two ways, either directly away from Earth on the other side because of some sunspot group and flare that happened back there, or it's aimed directly at us. And that's what we do as forecasters, utilize all our tools to help us figure out where it came from and where it's going. And hopefully we'll get it right. The fastest they can get here is about 15 to 18 hours, but usually they're slower movers and take about 2 to 4 days. When they hit our magnetosphere with force, if they're strong enough, they can push it all the way back in so that the GOES satellite, which normally is well within inside the magnetosphere, can finally find itself on the outside of the magnetosphere. It pushes it in before it rebounds back. And that's what you're seeing here in this magnetometer plot from the GOES satellite. So what does this mean? Well, this is what can cause geomagnetic storms. This is where the power grid, this is probably the most wide-ranging impact effectual event that we have with these geomagnetic storms. And what does this mean? Okay, this chart looks a little complex, but let's make it as simple as possible. The red lines are Earth's magnetic field, coming out the bottom of our planet, going into the top, a thumbs up orientation, pointing northward. Okay, the sun's CMEs, for example, that are carrying a strong localized magnetic field along with it, that can be in any direction. So what happens when you take a positive and positive magnet, try to put them together? They repel, right? Same thing here. If this magnetic field of the storm coming from the sun is oriented the same as Earth when it gets here, it may punch in and give us some immediate response, but generally it doesn't connect. It can't connect. It kind of repels it in a way, and we don't get any buildup of strong activity. But if it's facing the opposite direction, boom, the positive and negative magnet, so to speak, have connected, and now this can really drive and spin up geomagnetic storm events. Here's an example of a CME hitting our magnetosphere, or in this case, it's about 1 million miles from Earth that the instrument lies that we see this happen. You can see how the speed went from, we were in a coronal hole, obviously, the speeds were somewhere around 500 kilometers per second. Wow, the speed went up to almost 1,000 kilometers per second in an instant. The magnetic field got crushed. You see how that really went up. Normal magnetic field strength is about 5 nanotesla out there around that 1 million mile point. This went up to 20 plus. That's an incredible force when it comes to a magnetic field slamming in Earth. So when we see these and we analyze for them and we're looking for them now to hit, because when they hit that platform 1,000,000 miles from Earth, we can send out our warnings at this point if we think it's going to cause the response here at Earth on the magnetometer network and drive a geomagnetic storm. That's one of the models we use on the bottom right. That is too complicated to talk about at the moment, but that is the driving, our main and only real source of helping determine whether or not a CME is going to hit Earth or not. And if so, when that might be. But as far as the level of activity that's going to be, it's very difficult, very subjective call. So what does this do? Let's focus on the power grid. They want to know when we start to get the levels of activity here, because this can cause currents, electrical currents to generate on their systems, on the power lines that don't belong there. And what's happening is a direct current is getting introduced onto an alternating current system. That is not good. Those don't work together. That can cause all sorts of problems. And if the system gets overloaded with that direct current, it can cause giant expensive transformers to fail. And it's happened in the past. That's a severely damaged one down the bottom right. And these things are huge. They'd occupy more than my room that I'm in right now. And they're not off the shelf. You have to build these again. So the fear is we don't want to have a storm of this extreme in nature knock out our power grid if it was going to do so. One of the models we use to help identify the currents now is rather new. It's only been around a couple of years. One of our local doctorates right here at SWPC, Dr. Chris Bulch, helped work on this model. And this kind of gives an idea of the voltage being generated across the system. And there's a lot more that goes into that. I wish I had more time to talk to you about how that all works, but it's really fascinating. We may get to the point where we can actually send out more localized geomagnetic storm warnings in the future. So what does this mean for us? It means we get busy. We're busy with a lot of things we've talked about, but in this case, we get to be the busiest because we go from making a few phone calls on G1 levels to making more calls to suddenly being on a conference call with the entire North American power grid at just G3. We're talking to FEMA, the emergency response portion of our government at G4. And oh, by the way, very soon we're going to be talking to the Situation Room at the White House when we hit G5 levels, because they are concerned about what this could mean, especially in a long duration event, to the durability of our power grid. We're not talking about a failure in a town or even a county. We're talking about states that could experience this problem if it was to develop. And how does this measured? Well, I'll give you the scale, but in terms of history, going back to some of the history questions we had, well, in the 1800s, an astronomer was observing the sun, drawing a sunspot group, and he actually noticed a flare. He didn't know about flares at the time. To him, it just looked like an enhancement in white light because that's what he was using, projecting white light. So he noted it on his drawing that you see. That's that little white kidney bean shaped area around the sunspot group. Well, about 18 hours later, all heck broke loose around our planet. We had telegraph lines then. Batteries were starting on fire in these stations. They didn't know why. The aurora was seen all the way down in the Caribbean islands. People thought the sky was on fire. There's a documented conversation between two telegraph operators about how they're having problems and how they better disconnect their equipment. So they did. They still had a signal. They still carried on a conversation with no electric power hooked up to the system. That's the intensity of the storm. So this is called the Carrington level event for that astronomer who saw the white light flare. We've had a recent example of something that probably would have been that level event back in 2012. Fortunately, it went sideways. It was not aimed at Earth. There's a lot of information on this slide, but that's probably the most recent likely event that could have, if it hit Earth, probably registered up to that Carrington level type event. So here we are in our march up the solar cycle. We're ahead of the curve. We're still ahead of the curve, even though I took this picture earlier in 2022. Right now, we're still almost the same amount above that curve, just higher up on the plot now. And you can see where solar maximum is predicted right around 2025. And with that said, leaving time for some questions here. And these are points of contact if you want to have more questions in addition to myself, my boss, Rob Steenberg, and our program coordinator, Bill Murtaugh. That's been my pleasure, and I'm happy to take more questions.
Shawn, that was just incredible, and I am saturated with information. This has just been fascinating, and I appreciate your energy and sharing this information with us too. We do have a few questions already in the chat, so let's go ahead and take a look at those. The first one is asking, is the solar magnetic field related to ferrous materials, or is it more electrical currents in the plasma?
That's something that they're still trying to understand, because the interesting thing about the sun's magnetic field is kind of in its relationship to all that outer plasma, especially around the corona. I don't know the answer to this question at all, but it does drive another point of the mysteries of the sun, because the sun does something funny. Obviously, it's a million degrees plus in the core of the sun, that nuclear furnace. And then it slowly drops in temperature, as one would expect, till we're down to about 10,000 degrees at the photosphere. Well, then it starts to heat up again tremendously. We get to millions of degrees again by the time we're in the corona. And they're still trying to understand why that is. And one of the things they think is going on is the interaction of all these magnetic fields and all the different types of energy and radio waves, electromagnetic waves, and actions that are going on tend to heat up those areas of the sun. But I don't know the direct answer to this question. I won't even try to guess, but it just gives you more idea of the mysteries that we're talking about here.
So let me give you a question then that you'll certainly be able to answer for us. How do you become a space weather forecaster? What was your career journey into falling into this role that you have today?
Yeah, thank you. Before I tell you mine, because mine is strange. Mine is a very oddity. Normally, to get in this business, one would work their way through school and generally probably get a physical sciences type of degree or a meteorology degree. Generally, that would be the path. Usually master's degree or on up, but that's not what really happens, because dedicated programs to space weather just don't exist in university. There's a class or two. There's really not an academic program, a curriculum dedicated to this business. And frankly, there's not really probably enough entities out there doing this work. But my path is quite different. Mine actually came through the Air Force. So I signed on. I was going to college to be an environmental scientist. And after 2 years, I decided I want to join the Air Force. So I bailed and I joined the Air Force and was going to finish my school while I was in what ended up being, what I thought was going to be 4 years. 22 years later, I retired from the Air Force, but got into the meteorology side, not through a degree, but I ended up taking all sorts of classes, especially more and more in physical sciences, because my interests has kept changing. And then when I got out, I took a job as a forecaster doing meteorology for the Air Force for 5 years. And then from there, I got into the weather service out in Hawaii and eventually here. But while I was in the Air Force, that 4 years I talked about on Puerto Rico, well, 2 years after that, I was doing space weather forecasting over in California at the air base there. So all the extra schools, all the extra education that I received through those programs got me not only the academic levels one needs to do this, to be able to apply for the job, but it also got me loads of experience. So that kind of well-rounded figure got me to where I am. So I took the very long route to get here. The faster route would be do it directly through school and then look for a career into this.
Thank you for that. I'll grab another question from the chat here. Can human behavior or habits have an impact on space weather?
No, not really, not in that sense. We can't impact space weather by any stretch because the sun's too powerful, but we can work on mitigating it. And certainly as we become more technologically savvy, there's going to be more risks to space weather affecting our behavior because of the impacts we have on our technology, or in some cases, physical safety, such as the astronauts out there. They're going to be on the next Artemis mission. I mentioned I'd tell you what they're going to do. So I'm sure many of you or most of you have heard the phrase duck and cover. I hope you have, because the Air Force, the Weather Service really promotes that when you're stuck out in the lightning storm out in the open. You're just supposed to get as low as possible to the ground, cover up your head and duck and cover, not run under a tree. That's the last thing you want to do. Well, in space, when these astronauts are out there, they're on this tiny little capsule called the Orion capsule. And what they're going to do, there's going to be 4 astronauts on there. And there's going to be 2 safe areas, kind of, but they have to build them. So what they're going to have to do is they're going to have to take off a floor tile from in the capsule. They're going to have to get down in there. 2 astronauts are going to have to crouch down in there and then pull supplies around them as another protective barrier and cover that up. And they're going to have to sit there squashed up like this in this position for as long as it takes until we say the threat is over. The other 2 are going to have to go into the bathroom part of the tiny little capsule. So it's not going to be far away, right? We're talking about crammed space, and they're going to have to do something similar, surround themselves, whatever supplies are there. So that's what these poor astronauts are going to have to suffer through. And the level of events we're talking about are the much more energetic protons, not the ones that we measure for our normal warnings, but much stronger levels of energy, because that's really what drives these radiation storms that could affect human tissue and cause problems in our bodies.
So you mentioned during your presentation about the warning system that we have in place here on Earth, where you have a watch and a warning and alert for these storms. I have to admit, maybe I'm listening to the wrong radio stations, or the stations are getting knocked out before I get these alerts, but where can we pick up these alerts, and where are they promoted and advertised?
Yeah, generally, it's probably just going to be by going to our webpage. So swpc.noaa.gov. That is the webpage. Almost everything I've talked about is available through there. One can look at stuff on their own and kind of see what's going on, read more details in our forecasts and our discussions. But yeah, you don't hear the local, what you'll hear about from the local weather station on TV, broadcast meteorologists on occasion, is probably about the aurora. Hey, there's going to be a chance to see the aurora tonight. And they're getting that information from us based off our forecasting of geomagnetic storm potential, or a watch that we put out, or something we put out on Twitter or Facebook. That's where that comes in. That's usually the only time on TV you're going to hear about it. The problem people need to be careful about, especially today with this really social media driven world that we live in, is these things can get spun way out of proportion really fast. So if you really want to know what's going on, if you hear about a piece of the sun blowing off into space and just some crazy stuff, and just go to our webpage and start there as a basis of fact of what's going on, and then go further into details onto reliable sources as well from there.
Excellent. That's great advice. Our last question in the chat here is asking how many satellites could be disabled by a single space weather event?
Yet to be known. These are so rare, but they have happened. I don't know how many over time, but there's been more than several since we've been in the satellite age. And these are, it costs millions and millions of dollars to build a satellite, and then more to launch it into space, and then even more to get it controlled to the area of orbit that they're going to have it at. So usually I don't know of any time where more than one's been knocked out from a, say, solar radiation storm event, which is really the most impactful to these. But just recently, this year, SpaceX launched a train of satellites out there, 30-something satellites. Unfortunately for them, they were looking at the wrong information, and they didn't see the fact that how the geomagnetic storm, even though it was at a low level, was impacting the ionosphere. And what happened is about 75% or more of those satellites decayed instantly and were lost. There's a paper that a lot of our SWPC scientists, Dr. Su-Wei Fang is one of them, was involved in doing a paper on this whole thing. So if you're curious about it, that's out there now and you can look that up. But that is an enormous amount of satellites, right? And it wasn't even something that we normally associate with it causing a direct satellite problem. So yes, 25 or more have happened in one shot.
Oh my goodness, you have given us so much to think about, reflect upon, and I think I've encouraged all of us to go to your website and certainly look up, read some more, and keep alert of all of this. We are at the end of our time right now, so I certainly want to thank you, Shawn Dahl, for all of this information and the wealth of knowledge and your enthusiasm that you're sharing with us this evening. And Jeremiah, I'll turn it back over to you.
Yeah, thank you just once again. I'd like to thank everybody for coming. I'd like to thank Shawn for presenting. I'd like to thank NOAA for giving him the time to do so. What a great example of great science that's produced by our national science exploration and technological expertise. So I wanted to highlight that and thank you one last time. Please, everyone, come back for our final Zoom lecture on February 13th. And other than that, have a great night. Thank you again, Shawn.
Thank you, everybody. It's been my pleasure. Bye now.